Okay. Hello, everyone. Welcome to our ESIC seminar for today. We have with us Dr. Mona Ghassemi, who will be talking to us about conventional and emerging unconventional power systems, challenges and opportunities. It's my pleasure to welcome Dr. Ghassemi, and hopefully I'm not butchering your name, Mona. So,
Yeah, yeah, Ghassemi, which is good.
Ghassemi. Okay. Okay, good, good. I did a good job. All right. So I'll briefly introduce your bio. Read your bio. So Mona Ghassemi received her MSc and PhD degrees in electrical engineering from the University of Tehran. From 2012 to 2015, she was a postdoctoral fellow with the High Voltage Laboratory at NSERC, Hydro-Quebec, UKAC, as industrial chair on atmospheric icing of power network equipment and the Canada Research Chair on Power Network Atmospheric Icing Engineering at University of Quebec in Canada. She was also a postdoctoral fellow with the Electrical Insulation Research Center, Institute of Material Science, University of Connecticut in USA from 2015 to 2017. In 2017, she joined the Department of Electrical Engineering in Virginia Tech, Blacksburg, as assistant professor, and in 2021, she was appointed as both the Stephen O. Lane Junior Faculty Fellow and the College Engineering Faculty Fellow. She has been a registered professional engineer in the province of Ontario, Canada since 2015. Her research interests include electrical insulation materials and systems, high voltage field technology, multiphysics modeling, electromagnetic transients in power systems, and power systems analysis and modeling. So Dr. Ghassemi is an at-large member of Administrative Committee of the IEEE Dielectrics and Electrical Insulation Society from 2020 to 2023, a corresponding member of the IEEE Conference Publication Committee of the IEEE Power and Energy Society, an active member of several SIGRE working groups and IEEE task forces, and a member of the Education Committee of IEEE DEIS and PES. She was a recipient of 2020 Continuation Award from the High Voltage Journal, the 2020 National Science Foundation Career Award, the 2020 Air Force Office of Science Research Young Investigator Research Program Award, and 2021 Department of Energy Early Career Research Program Award. She's an associate editor of IEEE Transactions on Dielectrics and Electrical Insulation and IEEE Transactions on Industry Applications, High Voltage, the International Journal of Electrical Engineering Education and Power Electronic Devices and Components, and guest editor for Energies. So let's welcome Dr. Ghassemi, and Muna, it's on to you. Thank you.
I mean, thank you so much. I didn't recognize that it's a very long bio. I need to cut it down. So thank you. I mean, thank you for the introduction, Anamika, and thanks for having me here. So I will be talking about conventional and emerging unconventional power systems, challenges and opportunities. I don't have an outline because I didn't know how much of the things that I want to talk I can fit into this talk. So, and at the last moment, I had to, just cut the HSILs from the talk. So, but for now, I will be more focused on the high voltage engineering and dielectrics and electrical installation. For that one, I will take your attention to this, that by 2030, it is expected that all electric power will flow through power electronics. And this power electronics, they can be either part of they can be either part of that system or interact with power electronic systems for the power flow or control. The example for the power flow and control, you can see those here for the facts, HVDCs, and other things. Or it can be the interface with generation, load, and storage equipment. And the example for that is plug-in hybrid electric vehicles, renewables, and energy storage devices. That we all know that the very good example of that, it can be realized through microgrids. So besides these grid applications, we see power electronics that they have been targeted for the electrification system of other application. For example, this is for the medium voltage distribution system that has been targeted by U.S. Navy for the all electric ships, and there are other existing and also future applications that will benefit and that they are benefiting from power electronics, which are one of them are the ultra deep water, oil, and gas electrification, which is not only for the gas and oil electrification, but also for marine type of renewable energies. And this is another example are transportation, which is for all electric vehicles, for trains, and for more or all electric aircraft. So you see that the power electronic will play a great role in the future of the electrification. So on the right side, I have the figure that this is the space that is associated with the silicon performance. If you have this red line, this is the limit of the silicon operation. And this area is the area that the WBG power modules that, we all know about the SiC, gallium nitride, gallium oxide, and diamond. And we know that they can be operated at higher powers. So this is the power, higher powers, and higher frequencies. So, well, of course, the silicon devices, they cannot operate in that space. So, and there are opportunities that can happen when you use WBG systems, which can operate at higher powers and higher frequencies, which silicon systems cannot. Okay, if there are opportunities, and we know that the WBG power modules, they provide a more efficient, lighter, high temperature capable, and also they can provide a smaller, we can have a smaller power converters if we use WBG power modules. And it may seem that, okay, everything is okay, and the future is very bright if we use this WBG-based technology. However, there will be a dramatically increased number of power system apparatus failures in motors, generators, and power transformers and cables. So that may lead to brownouts or maybe blackouts. So, and this will be the case for all the, systems for that are using WBG based conversion systems, like electric vehicles, aircrafts, ships, because they all use these WBG power modules. The question that you may ask is why? Is it because of the cyber attacks, or is it because of the power system requirements like voltage or transient stabilities? The answer is no, it's not because of that. The answer is this happens, that failures of the power system apparatuses, that happens because of the accelerated aging of the insulation systems, that happens under fast repetitive voltage pulses that are coming from those WBG-based power electronics. And this is expected to be the most significant barrier to acceptance and realization of WBG-based systems. So let's see what exactly I mean. I mean, every electric device has two main components. Well, if you consider electric machine and transformers, you can say has three components: magnetic materials, which are for electric machines and transformers, and insulation and conductors for all other electrical devices. So when we talk about a failure, I have some picture of the failure of the power system equipments here. When we talk about a fault in power system, this is often related to the failure of the insulation of an apparatus, and not, for example, failure of the conductor or magnetic material. So here I can make a statement and I can say the life of any electrical apparatus is determined by the life of its insulation. So most of the time. So okay, then it looks like that the insulation, electrical insulation, or the Achilles heels here. However, you may say, okay, if there was any problem, it should have been solved by today. Well, the answer is yes for the traditional power system, yes. However, is the question is, okay, what is the problem now with the current insulation materials, and what are the technical gaps? This is for the now and future. So the answer lies within the current and future trends that exist, exist now, and the materials, insulation materials that we have now, they cannot meet those requirements. So the first trend is toward more and all electric apparatuses, and I would say more electrification. This lead to higher electrical demand. So this is the first trend, higher electrical demand. Another trend is toward reducing the size and weight of the component. This lead to high power density designs. So when we have increase in the electrical power demand, we can either provide that by higher currents or higher voltage. So you can either go higher currents, higher voltage. Well, we don't go to the higher current because of the voltage drop problem and the weight problem. We don't go to the higher current, so we go to higher voltages. Okay. Now, if you consider this high voltage and then combine that with the high power density that we are looking for, it will be resulted what I call high voltage, high power density concept. Okay, now you have a combination of the high voltage and high density, which will result, if you have the high voltage and the high density, it will result on the high electric field. If you combine the high power and high density concept, it will result into higher temperatures. And there is another trend, and that's the new trend that we see, and that's emergence of WBG switches in electrical conversion systems. And this is another trend. So we know that one of the merits of this WBG-based systems are that their slew rates and the switching frequencies are much higher than SI-based systems. However, if you see that from the insulation side, frequency and slew rate, these are the two most critical factors of a voltage pass that influences the level of the degradation of the insulation, which are exposed to such a voltages. So if you combine these three factors, and those are the high slew rates and high repetitive voltage, high electric field, and high temperature, you will have a very bad working condition for any insulation material. And since we are taking this equipment to a spacecraft and to aircraft, we are adding two environmental challenges to this already three challenge that we had: high temperature, high electric field, high slew rates, and high repetitive voltages. Then you will be adding, okay, low pressure and harsh environment, which it can be from minus 60 degrees to 250 Celsius degrees, and the low pressure. And the combination of all these factors will be extremely bad working condition for any insulation material. So these are the challenges that we face, and we need to think about those challenges to find a way to mitigate those. So the most important challenge that I see is I will take you to an example. If I want to go to more detail, I will talk about the insulation degradation because of the internal partial discharge that we see in solid dielectrics. So first thing is that we can divide the insulation degradation into four factors. One of them is a space charge, intrinsic aging, tring, and partial discharge. The PD or partial discharge has the most effect on the degradation of the solid dielectrics, and it's inevitable because we cannot have the dielectrics without defects, without voids and cavities. There is no such a solid dielectric. So that's why PDs are very important. PDs themselves, they can be divided into surface charge, corona, or internal discharge, which this internal discharge is the most important one that we see in solid dielectrics. So I want to show you that what happens if you go to higher frequencies and higher slew rates. So here I have a figure. Here I have a figure. If you look at the figure shows the average lifetime of a single contact point across enamel wire. So as a function of both frequency and the rise time of the square wave voltages. So here we consider this square wave voltages is kind of relevant to the voltages that are coming from this WBG based converter. So for the simulation, we use that square wave form voltage. So here you can see that as I increase as I increase the frequency, the lifetime decreases, and also you can see that as the rise time gets shorter, the magnitude of the PD gets larger, and you will have the shorter lifetime. So that will affect the lifetime of the insulation greatly. So here, although we know that WBG devices, they can lead to high power density designs, we see that their generated voltage pulses, and this is only one example. I can bring you many more examples. So the generated voltage pulses, it can pose a severe threat to insulation systems. So I have another example from this reference that shows that the risk of component failure can happen even hours after, using those WBG-based conversion voltages. For example, here a failure time of around 50 working hours was reported when there was an induction motor that was fed by a PWM inverter, and the frequency was only 10 kilohertz. And we know that the systems, the WBG power systems, they are targeted for 100 kilohertz. And so you can see that what will happen at 100 kilohertz. So here I have another example to show you that if you take any electric component to the aircraft, to the spacecraft, the situation will be worse. So we developed a FEA model for PD. Here, the case study, I have two spherical electrodes. One is HV, one is grounded electrode. And we considered that we have an air-filled cavity in the silicone gel between two, electrodes. And the results are very exciting because it shows that the minimum cavity diameter that you see here that can causes PD at different pressure levels. You see that this is the pressure, and this is, you see that the voltage that PD starts at each of this. So these are the actually not voltage, it's the electric field that the PD starts. So you can see that as the pressure drops, you can see that the size of the size of trouble making these voids shrinks. So means that when you are on the higher altitude, even very, very small, voids can be troublemaking. And also we can see that the mean true charge based on the pressure and the mean PD duration, they both increase when you go to higher altitudes. That translates to higher PD duration and intense PDs at higher altitudes or at lower pressure. So this is what we deal for the all electrification in aircraft and spacecraft. So what is the challenge here? The challenge is that the research that has been done up to date, it's limited. If you go to the literature, it's limited to few kilohertz the frequency, and the slew rate is to few tens of kV per microsecond, which is for the SiC based power electronics. This is what has been done. And if you go and you look at those literature, you cannot find any physical based explanation or model that presents that they got from the test results. So we don't know what happens under few hundred kilohertz or few hundred kV per microsecond. And this is our target. This is our target for all electrification in aircraft, in ships. And when I say we don't know what happens, means we don't have any experimental investigation. We don't have any modeling and simulation, and we don't know what are the novel dielectrics and insulation systems can be used to mitigate those effects. So, for example, here, one of the materials that we worked on, this is an example, is nonlinear field dependent conductivity materials that we introduced this for use in power module packaging, and also using high temperature dielectric liquids instead of silicone gel in power modules. So because of the tremendous importance of this subject, a secret working group formed recently, and we have three subgroups there. One of them is rotating machines, one of them is transformers, and the other one is electronics. I'm the chair of electronics, where we see the effect of accelerated insulation aging from inside power modules and power converters that are caused by WBG-based converters, WBG-based power modules and converters. There's also another IEEE task force. It just formed very recently. We had just our kickoff meeting, I guess 2 or 3 weeks ago, and it's for transportation electrification. So these are the activities that are going on in this area. So to tackle the problem, I have an approach, and I will call that approach a theoretical based multiphysics modeling. This is a very beautiful area, of course, for me, that you can go inside the physical phenomena that happens behind pre-breakdown. I see it as an edge between engineering and science, and this is the approach that I think that is needed for the optimal design of electrical insulation systems, especially because of the trends that I mentioned in previous slide. So this is this physically based theory approach in all physical mechanisms behind pre-breakdown, they will be considered. I see that the future of the electrical insulation design belongs to this approach, and this will lead to reliable, compact designs. And if you go to the literature, you see that there isn't that much effort in that area. So you probably find very few papers that are dealing with this area. So there are some steps that you can take to achieve this approach. The first is identifying all the physical mechanisms behind pre-breakdown phenomena in the media that you are looking for to study, if it's gas, if it's liquid, if it's solid installation materials. So I have worked on gas and liquid previously, and now I'm working on solid installation materials. Then you need to develop a set of mathematical equations to describe those mechanisms, then develop numerical methods and address their numerical issues to solve the equation. Of course, you need to validate your approach by experimental data. And this is where it's cheaper. If you go to the traditional work, we always do experimental data. And when you want to design a system, you cannot do the experiment on a real geometry. So it will be very more of an estimate, and I would say overestimate. That's why if you have a model and you can validate your approach by experimental data, it's very cost effective and it's more reliable. And then implementing approach as an engineering tool for the design of electrical installation systems. So this is my main goal. I would like to have an engineering tool that I can design the electrical installation systems in that. So of course there are some difficulties, which are the complex theoretical concepts, then mathematical equations, they are complex, then you will face numerical issues to solve nonlinear extremely coupled equations. And the last one is the least important one, which is the need for high performance computers with huge memory resources. So these are some challenges. So here to show you the one of examples I have here an example. I did this for liquid dielectrics to design HVDC Wetamate connectors. So these Wetamate connectors, these are needed. You need to have to those to reconnect the repaired modules to the grid at seabed. You see that these are DC connectors here. So you need to have them to be able to do the repair. And you can use that for the oil and gas electrification process. And also you can use that for the marine renewable energy. And so it can have two applications. So we need both HVDC and NVAC Wetamate connectors. So as of AC connectors, they are already commercially available, and the voltage up to 36 kV. It's called Meccan. It's for GE. However, there is no commercially available HVDC Wetamate connector. And in that project, actually, we designed the first HVDC between 50 to 150 kV, and as the funding comes from RPC and NETL. So here in the next slide to show you what I have time, okay, to show you what a Wetamate connector. I have a video. So in this video, the video doesn't have a voice. So in this video, we can see the different steps of mechanical and electrical mating. This is for a Meccan, which is an AC connector. So what happens, this is under sea. So you have salt as well as other, ionic species inside the seawater. So you have to first remove that seawater between two contacts after mechanical mating, and of course before electrical mating. And then you need to clean the area in between and fill that area with a liquid dielectric, and then make the electrical connection. So here we have now different. You can see the different mechanical mating and happens. Now you see that the chamber, this chamber is flushed with high velocity seawater that is to remove the particles. After that, um, they will use fresh water to desalt, which should happen now. You need to have the fresh water, and after fresh water, um, you will clean it with ethanol. And after this, you eventually need to fill the chamber with oil, dielectric oil, um, which is the electrical insulation in this system. So the whole purpose of this project was choosing the proper dimensions and materials for the insulation system in a way that the criteria that I choose was I didn't want to see any streamers that happen to in a liquid dielectric under both normal conditions and especially under transient conditions, transient overvoltages. So that's the most conservative way of taking no streamers. Of course, we know that you can have streamers, but there won't be any electric breakdown there. So I can continue, and to establish this method that I call theoretical based multi-physics modeling. First, as I said, we need to identify physical mechanisms behind pre-breakdown phenomena. So in this Vetemate connector, we have a hybrid solid liquid geometry here. So I did evaluated electrical insulation performance of this Vetemate connector under impulse voltage. Okay, so there are three mechanisms that may lead to increase of free charge carriers in a dielectric liquid if you highly electrically stress that. And they are charge injection or Fowler-Nordheim charge injection, electric field dependent ionic dissociation, and electric field dependent molecular ionization. So based on the simulation results, we could show that electric field dependent molecular ionization, which is the last one, captures the vast majority of the physics that associated with the streamer development in the transformer oil. Here it's a transformer oil. So that's the mechanisms that we choose. And then regarding that physical mechanisms that I chose, I could develop a time-dependent thermoelectrodynamic model that you see that I have a Poisson equation and I have three charge continuity equation, each for positive ion electron and negative ion. And I also have a thermal diffusion equation. I wanted to see the temperature. This is something that I added. You don't need to have that one for this kind of evaluation. And so since I considered the field electric dependent molecular ionization mechanism here, I did choose the source and sink terms based on those. So there are the attachments and the source and sink terms that you see here. You choose those based on the electric field dependent molecular ionization. And there are also some other steps and details when you develop the numerical methods, and there are some numerical issues that you need to solve, and also you need to validate, which I did, the validate the model with experimental tests. I do not go to all those details. You can find those in my papers. So this is how I developed a mathematical model. And then here I have only one slide to show you the outcome of that study. So here you can see that I have the HV electrode here. This is the HV electrode. So this is the solid insulation, and this part is the oil. So here in this four figures, you have that in four different times. You can see the movement of the charged particles. So this is the movement of the charged particles, and the solid dielectric is PTFF. I consider that, and the applied voltage is 300 kV for this slide that you see here. So you see for this voltage level, I see a bubbly like streamer. So this is I call a bubbly like streamer that is formed and propagates through the oil. I also could find the speed of the streamers. It's very important when you deal with streamers to know the speed of the streamers. So if you want to find the speed of the streamer just across this line, this is these are the lines of the electric field on that point, and then you can find the speed of the streamer, which is 1.7 kilometers per second. So based on the speed of the streamer, we have four types of the streamer. So this is the least dangerous streamer because it's a low speed. You can have streamers up to 100 kilometers per second. And to give you a sense of 100 kilometers per second, you know that the atmosphere, the length of the atmosphere is 10,000 kilometers. So if you have an electron on the streamer that is the speed of a streamer is 100 kilometers per second, it means that it will go out of the atmosphere in 100 seconds or 1 minute and a half. So you can see how speedy can be the streamers and how dangerous they are. So then I considered, I had the model, I validated the model with a geometry that I could, do the test. Then I take the model into a real geometry, and I try to apply four mitigation method. I use four mitigation method. I don't have those, but I have. You can find them in my papers. So I wanted to show you here that the approach that I use, it can be a powerful engineering tool to design a reliable, compact component with which is of course very, very much less expensive if you want to do the test for all the configurations, and it's not even reliable. Another topic that I would like to talk is about emerging unconventional power systems. And these are future power systems for all electric ships and aircraft. So in conventional power systems, we have three things that are fixed: AC, the frequency of them, and the voltage level of them. So in each country, we have the standard voltage level. These are the for US. The frequency can either be 50 or 60, and the AC is the system that we use for our, traditional power system. However, when we talk about the future power system for all electric ships and aircraft, these three parameters, they can be variable. So, and also the two factors that are not important at all for a conventional power system, which are weight and size, they are very important for electric ship and electric aircraft. So we can have a, kind of, we can have an optimized, version of a power system, using, what type of voltage we want to use, what frequency we want to have, what is the voltage level, and we want to have the less weight, and of course we want to have the compact size. So there is one RPA project that I am leading, that's connecting aviation by lighter electric systems or cables. And in this effort, we're gonna design a medium voltage DC cable for an aircraft. So why did we choose DC here? Because it leads to more weight reduction and loss reduction. And also, however, this is for aircraft. I should mention that DC is more compatible with the nature of some of the loads that we have, especially for Navy. So the first problem that is there is that we need to have power flow solver for DC networks. Second challenge is that cables should be used, the cables that they will be used in harsh environments like low pressure, high humidity, high temperature, and so they are not the similar as the underground cables that we use on conventional power systems. This means an opportunity to explore new electrical insulation and thermal management ways. This is both opportunity and challenge. And another challenge is that to reduce weight and size. So that means that, as I said on the very first few slides, that means that you have higher electric field and higher temperatures, and then you add this all harsh environment. So this makes the problem very complicated. So here I have, because now we are working on this project, here I have some slides to show you that what we are doing for the all electric aircraft. So we considered the all electric NASA N3X. Of course, the NASA N3X is not an all electric aircraft, but we considered that as all electric aircraft. It's a wide body aircraft. And what we have done up to now, we could develop a DC load flow, and we chose several optimal EPS architectures for our all electric aircraft. So here I have them. So we use two methods, ZBus method and monotone mapping method for the DC solver. I don't have the equations here, but again, you can find those in our it just published paper. And so here we consider that, okay, we want to have a 10 kV cable. So we will have a 10 kV medium voltage grid. And so we considered positive, negative 5 kV medium voltage DC microgrid that is for an all electric N3X aircraft. So this is the system. Some of that is for NASA. Some of that is our, architecture. So, for example, this is our proposed architecture, because the NASA is not all electric. So we got the 25 megawatts of the power from NASA. They have 14 motors. We left that the same. And I go to the next one. If you want to do the power flow, you need to know the dimension. You need to know the dimension of the aircraft. We could find the dimension of the aircraft. This is an estimate. This is an estimate that we did for, so you have all the dimensions of the aircraft, because if you want to do the power flow, you have to have the dimensions. And so we did that, and then this is the case for we have the power flow results under normal condition. Okay, under normal condition. And what is the difference here that we considered for the power flow here, DC and AC? Well, if you remember, for the AC power flow, we had three types of buses. So you divide the buses. Either you have one slack, PQ buses, PV buses. So here you have a DC power flow, and means that you don't have a reactive power. So you don't have something as anger here. Cables, or I would call lines, they only have a resistance. There's no X, there's no C, because there's no omega. So we don't have the power angle. And we only have here voltages and current that are the same phase. So when you eliminate the angle, you can consider you have two kind of buses. You can either say it's voltage controlled, that voltage is constant, or you can say, okay, it's power controlled, that you know the power. So for here in this figure, this is very small numbers for bus 8 to 21. They are connected to the loads. Well, we consider that, okay, they are power controlled. Then you have the buses 1, 2, 3 here, and 4. So you can see, if you go to the table 2, we consider that I have bus 1 and I have bus 4, for example. I consider those as the voltage controlled buses. And for the normal condition, as I said, we have 20 megawatts of the power. This is for the takeoff. So we consider that 4 units of EUs, which are electrochemical energy units, and we consider all of them, they are the same, 25 divided by 4. So this is just to give you what happens. So here, what we did here is just the normal condition. So everything is in its place, and we did run the power flow for the DC, so we could find the voltages and powers, or I should say currents. Here on the table 3, you see that flows through the cables. Of course, what we did choose, we chose kind of the here, okay, what I chose for the conductors, they are the conductors that are for general cable. So because here I'm just on the design step, so we will use new type of conductors that general cable has, and we consider those. But I should say that when you talk about, that you take the cables that you use for the overhead lines, the conditions are much different, because for the overhead lines, they are bare conductors. You have them on the ambient temperature. You have wind. You have other means of reducing the temperature. However, I'm taking this to the aircraft. I will have an insulation over them. So the situation is a bit different and challenging here. I would consider at this time, because I'm not going to the design of the cable, I'm considering at this time just let's say 10% wiggle room between what you have on the data sheet and what you get from the load flow. So for the normal load flow, you see that if you go to the table 2, you see that the voltage, you don't have that much of the voltage drop. When in a power system, we know that you are allowed to have 5% below and higher than the 95% to 1.5%. Here you see all the voltages are very close to that 5 kV. Of course, this is because the system is small and the buses are not distant. We are not talking about power system that you have a bus here, the other bus is a few hundred miles away from here, so it's very small, so you don't have any voltage problem. About the power or about the current, as I said, what you have on the data sheet. Here, I just considered maybe 10% of the wiggle room between that one, because also besides of the insulation that you put on the conductor that blocks the heat transfer, you put all the system into a low pressure, and that means limited convection. So yeah, as I said here, the results are acceptable, and we could get a good normal condition. However, when you want to, in the power system planning stage, you need to consider also single contingencies. And this is the architecture that we proposed. And if you go through this architecture, we did the power flow for all of the single contingencies, and I don't have the results here, but it's good. So we came to this architecture as an optimal architecture of it's reliable when you have the single contingencies. I considered also the number of the circuit breaker failure. It happens, okay, if you order to a breaker to trip and it does not, so it does not open. We have a backup breaker for all of that. We have a backup breaker for all of that. Let's say if your this breaker doesn't trip, you have this backup to just trip that one. So we considered backup breakers for all of that. And another criteria that we use is to minimum the number of circuit breakers. Well, circuit breakers, I wanted to minimize the number of them for two reasons. The one is weight, the other one is the cost. So actually, you can come up with other architectures with more breakers, but this is the architecture that is reliable under single contingencies. If you have a circuit breaker failure, and also this has the only 68 circuit breakers. And when I'm talking about 68 breakers, I'm not considering this part that you need to breaker all here. You need to have the breaker after the converters, and you need and I exclude this part, which you need to have breaker when you are connecting EEUs, which are batteries, fuses, capacitor, supercapacitors. So I'm not considering all of those, and I'm talking about the breakers that you see here, because these two parts are the same for other architectures. So whatever architecture you come with, those are the same. So this is I wouldn't call that an edge configuration, because it's not really an edge. This looks like a ring configuration. This is the second architecture that we choose. Well, this has the 72 circuit breaker. This is another architecture that is another type of ring. This is not really ring configuration, and it only has 64 circuit breakers. So these are we are at this stage. We are having this optimal architecture. Next stage will be the design of the DC cables for this one. So this is an ongoing project that we have. Another challenge that we have is I have just 3 minutes, I guess. So this is the last one. This is the last slide. So another challenge regarding the failures that I talked about in insulation systems, power system, insulation system, is the assessment of the health of the insulation. And in this slide, my focus is on electric ships, but this can be the case for all electric aircraft as well. So we kind of consider the PD activity as the primary indication of weakness, any weakness in insulation materials. that we want to monitor that PD online for all electric ships and all electric aircraft because of the safety of the, because of the safety reason. So the future online PD assessment, we need to have three, I would call that three goals, which is detection, recognition, and localization. So for detection, it's very important because none of the PD measurement systems that are commercially available, they cannot detect PDs that are coming from excitation voltages that are more than few kilohertz. So the first challenge is innovation. I mean, inventing, a PD detection method here. Another challenge is that there are noise interferences. They are coming from external sources like IPEBs. IPEBs are integrated power electronic building blocks, that they will overwhelm this PD pulses and they will make it very difficult for you to detect PDs. Then there is opportunity and challenge here. Again, you need to recognize and localize the PDs in the, I'm talking about the, ship in a power corridor of a ship, in a power corridor of a ship. And there are three main types of PD, as I mentioned, and there are only even for one type of them. Let's say you have a PD coming from a void and only from one power cable, there might be several different locations along that cable where that internal PD, because of that void discharges happens. So indeed, we face a very complex environment where there is a large number of PD sources, and the input PD signal that we measure is the mixture of all PD sources. Then we need to separate and recognize multiply PD sources, that we are working on those. Of course, it's very difficult. However, using deep learning techniques, you can deal with those. And actually, we're working on the separation of the PD signals that are coming from corona discharges, from multiple, sources. And I don't have the reference for the paper that we have, but we just published a paper on that one. So this is another challenge that you see, in regards of the power system failures that happens inside insulation. I am sorry if I talked too much, and I really appreciate your attention.
Thank you so much, Mona. Very timely and impactful research. We'll take a few minutes to ask some questions, if you don't mind. And we're running a little bit over time, so I'm not sure how your schedule is. Are you okay with maybe a couple
I
of?
just need to, maybe
Okay.
a couple of minutes because I need to go and pick up my son.
Okay. All right. So let's say we have one on the chat, but let's see if anyone else. Uh, so would you please comment on the reliability of wide bandgap conductors based power converters in different applications, as some industry studies show that significant concerns compared to silicon power converters?
Excuse me, can you please repeat the question?
So the question is on the reliability of the wide band gap conductors based power converters.
Reliability of WBG
Yeah.
converters.
Yeah. So Sanjay, would you unmute yourself and maybe ask a question? I might not be able to explain properly. Let's see if he's still there. Uh, he dropped out. All right. So Maybe they were overlapping meetings, Mona. Sorry about that. Um,
No, I mean, he can ask me by
Yes,
email.
that's what I'm going to recommend, that he reach out to you over email and we can go from there. So I won't hold you longer since you said you have to pick up your son. Thank you so much for spending time with us and for introducing us to your research. This for students, if you have any questions for Dr. Ghassemi, please email her. Her email is already shared with the flyer and she will be happy to respond. I'm speaking for her, but yeah, go ahead, Mona.
Oh, thank you so much for inviting me. I'm writing my
Okay,
email,
awesome.
and it's
Awesome.
very easy. Unlike my last name, so it's just Mona G at vt.edu. And thank you so much for having me and spending your afternoon with me. It was a pleasure, talking about my research. And I guess I wanted to talk more, but I didn't have time.
We
And
will invite you next time. Thank you so much, Mona.
thank you
Yeah.
so much. Thank
Yeah.
you.
Have a great evening. Bye. Bye,
Thank
everyone.
you as well.
Thank you.
Thank